Now, two phenomena that you might see during the starting of induction machine is cogging and crawling. So, what are these? We will see one by one. First, if you see cogging, this will usually occur when the number of rotor slots is equal to the number of stator slots, or when it is an integral multiple of the number of stator slots. Okay, when it is an integral multiple of stator slots. So, what happens in this case is the rotor RMF is going to coincide with stator RMF. So, we know that the rotor RMF as well as the stator RMF, they both rotate at synchronous speed. But what happens? There is a lag. So, that means if this is the stator and this is the north and south pole that is produced because of the stator RMF, that is because of the stator windings. Okay, so this is the stator. Now, the rotor also will produce its own poles. Now, when the north pole is slightly lagging, then what happens? As the stator RMF rotates, the rotor RMF also it will try to rotate. Okay, and because there is a lag, this rotor itself will have mechanical rotation, so that it is always trying to catch up with this north pole, the stator north pole. Okay, but what happens in cogging when these both coincide? So that means instead of there being a lag, it is going to exactly coincide. In that case, what will happen? They both are in the same position, they are coinciding. So this will rotate at synchronous speed, this will also rotate at synchronous speed. There is no need for the rotor to rotate. Okay, so that is what as cogging, and sometimes it is called as magnetic locking. Okay, so this is one problem during starting. So you can write, since the rotor RMF coincides with the stator RMF and both the RMFs rotate at synchronous speed, then the rotor will not rotate. So now how to avoid cogging? We simply shouldn't let this happen. That is, the number of rotor slots should not be equal to the number of stator slots or the integral multiple of stator slots. Now what about crawling? Here also it depends on the design only. So what happens here? This problem will occur because of harmonics. So we know what is fundamental harmonic. If this is the frequency, that means if f is equal to 50 Hertz, then this is the wave for 50 Hertz. Now what will be the second harmonic? The second harmonic will complete 2 cycles in the time this completes one single cycle. That means it is going to be like this. Okay, so 2 cycles are being completed. So this is the second harmonic. What do we call this? This is either called as the principal or the fundamental harmonic. Now in an induction motor, you are predominantly going to experience 5th and 7th order harmonics. So the effect of these harmonics will be predominant. Now what happens? The phase sequence of fundamental harmonic, if it is like this, this is phase A, B and C. This is the fundamental harmonic, let us say. So this is what we call as the positive sequence. Now what happens with the 5th order harmonics? If the phase is A here, since the fundamental harmonic has 0 phase, this 5th harmonic will also have 0 phase. 5th harmonic. Now second phase is going to have a phase of initial phase of 120 degrees. So 5th harmonic will have 5 times 120 degrees. So what will be 5 into 120? It will be 600 degrees. So if you reduce it to a value less than 360, what will it be? It will turn out to be 240 degrees. That means minus 120. So B is going to come here. Similarly, C is going to come here. Okay, 5 times 240 will give you plus 120. So here you are going to have a negative sequence. Now, seventh harmonic, what happens in seventh harmonic is you are going to get once again a positive sequence. So this is A, B phase you can get if you multiply 7 into 120. So this is going to give you 840. Now 840 minus 360 is 480, still it is greater than 360. So once again if you subtract, you are going to get 120. Okay, so that means B phase is going to come here. Similarly, if you calculate C phase, how will you calculate C phase? 7 into minus 120, or you can take 7 into 240. And in a similar manner, if you see, you are going to get 240 or minus 120. Okay, so this is once again a positive sequence. Now, what will be the speed of the RMF produced because of the fifth harmonic or the seventh harmonic? Here the number of poles are going to increase. That means if you consider the fifth harmonic, it is going to have 5 times more poles as compared to the fundamental harmonic. Okay, and seventh harmonic is going to have 7 times more number of poles that are produced. Okay, so what will be the speed is fifth harmonic poles rotate at ns by 5, where ns is speed of fundamental harmonic. Okay, so why is this? If you remember the formula, this speed is 120 f by p. So if the harmonic is number of poles is becoming 5 times, so the slip will become divided by 5. Similarly, seventh harmonic poles rotate at ns by 7, where ns is again the speed of fundamental harmonic. Now what about the direction of rotation? Since the sequence is negative for fifth harmonic, the torque is going to be in the backward direction. So these fifth harmonic poles will rotate in reverse direction, whereas seventh harmonic will rotate in forward direction. Forward in the sense the same direction as fundamental harmonic. Okay, so now what is going to happen when the induction motor is starting? It will tend to stabilize at this ns by 7 speed, and it will continue running at that speed itself because this is a stable operating point. So you can write down the torque produced due to the seventh harmonic poles may result in the motor running steadily at ns by 7 speed. Okay, so this is called as crawling.